Hello, in this video, we're going to be talking about the topic of almost commuting nearly commuting matrices. So we'll begin with some definitions. Suppose we have A and B that are n by n matrices. Define their commutator, bracket AB, to be AB minus BA. Define this to be the commutator of A and B. Next definition, we say that some matrices, so just some collection of matrices, n by n matrices, are delta almost commuting if AI AJ minus AJ AI is bounded in norm by delta for all I and j. So the idea is that their commutators, as what these are bounded in norm by some delta. So their commutators are very small, or small by some delta. Definition, so this is another definition. And then after we make these two definitions, we'll make some comments. Some matrices, so just same setup, some collection of matrices, n by n matrices, are epsilon nearly commuting if there are commuting matrices AI prime, such that AI prime minus AI, the distance of these two, is less than epsilon. So this right here is almost commuting, which is to say that AI AJ is approximately 0 in the norm here that we've chosen. And nearly commuting is that to say that AI is approximately some AI prime, where the AI prime are actually commuting. So these are measuring how nearby they are to being. So this is measuring how nearby they are to be commuting. This is measuring how much commuting they actually are. So what we're going to show is that being nearby commuting, from that you can show that their commutators are small, that they are almost commuting. Nearly commuting implies almost commuting. The converse is non-trivial and is kind of this topic that we're going to be talking about. So this is trivial, trivial-ish, and this consequence is the one that's very interesting, the one that the topic's about. What we'll do is we're going to restrict our discussion to the operator norm. So this setup here, you could ask this for any norm. So this is just a norm for matrices. However, we didn't say what kind of norm we're choosing. In theory, the kind of answers you get could depend on the norm. So what we're going to do is we're going to restrict our discussion to the operator norm, which is the operator norm of A. So matrix A is defined to be here. So basically you take any vector in Cn with length 1, and then you see how much it stretches it out when you apply A. And then what you do is you take the maximum value that you can possibly get from any vector. So basically, what's the maximum it can stretch out a vector? That's what the operator norm is. It also can be expressed in this dual formulation. And what is the dual formulation? Basically, you take AV and you do an inner product with W, where V and W are both vectors in Cn with length 1. So we're going to use another definition, which is sigma of A, which is the spectrum of A. When A is a matrix, it is just the eigenvalues of A. In general, it is defined to be the set of lambda where A minus lambda I is not invertible. So for matrices, that's the same thing as this thing being singular, which means that you have an eigenvalue there. However, for A belonging to some more abstract space, some kind of abstract algebra, where you're interested in these kinds of objects, this right here can be more complicated. So some facts about matrices. The operator norm is equal to the max singular value of A. If you're familiar with, this decomposition, singular value decomposition. The operator norm of A is just the operator norm of the singular value matrix in here. Unitaries don't affect the operator norm. You can check that by using the dual formulation here. And then the operator norm of this is just the max singular value. So the maximum diagonal entry here. In general, the operator norm is bounded above by the maximum of all the absolute values of the eigenvalues of A. But why is this true? Well, if you do AV is lambda V, where V is a non-zero vector, so what we can do is we can assume that V has length 1, and then you just take the norm of both sides. AV is lambda V, which is just absolute value of lambda. And then you do what you do is you maximize over all eigenvalues, and you get, well, let me just, on this side, you get this. So the operator norm is bigger than the absolute value of each eigenvalue, so you just maximize over the eigenvalues. So these are just some two kind of basic properties of the operator norm. A sufficient, but not necessary condition to have equality here would be that the matrix A here is normal. What that means is that A commutes with its adjoint. Its adjoint is defined to be the conjugate transpose of the matrix. So if your matrix is normal, then you get equality here. So the norm of the matrix is the maximum of its eigenvalues in absolute value. So in a lot of cases, the operator norm can be kind of difficult to work with if you're trying to calculate it explicitly. There isn't like a kind of nice way of writing down what the operator norm is. So for instance, if I just write down a 2x2 matrix, you can find the operator norm using eigenvalues. There's only 2 eigenvalues. And using the C-star identity here, we'll talk about that in a second. You can find the eigenvalues of a certain related matrix, and then you can find its operator norm. However, once you start straying into bigger matrices, having a nice expression for the operator norm can be very difficult, if not really manageable at all. So that kind of makes the operator norm kind of difficult to work with. There are other norms that are kind of easy to compute. However, the operator norm also has some other properties which are rather nice, which kind of make up for this in a certain sense. However, it's not like a question of whether or not one norm has nicer properties or such. The question is, for each norm, we have this question that we are looking at, almost and nearly commuting matrices. So for each norm, you have a different problem. But also, just because your norm doesn't have one nice property, it might have other nice properties. In particular, the operator norm does have other nice properties. So one of the properties is that if you take the operator norm of a product of two matrices, that's bounded by the product of the norms. So you can just break up the product here in terms of the product of norms. It also has the property that the adjoint is isometric. It doesn't change the norm of the matrix. So these two properties together, if you're in some kind of Banach space where you can do multiplication of the elements of the Banach space, give you what's called a Banach star algebra. The operator norm also has this other identity. It's called the C-star identity, which is that if you take the product of A star A and you take its norm, it's the same thing as the norm of A squared. It's equal to this. So all three of these are true. And you can parse up what you mean by the C-star identity by kind of deciding which one of these you mean. But the point is that all three of these are true. This is equal to this is equal to this, and this is equal to this. So if you take n of C, these matrices here with the operator norm, this gives you what is called a C-star algebra. And it has this star here. That's going to be useful later. However, for what we need right now, some of these just inequalities are just something to use. So the first fact is like a result what we're looking at is that if you have some matrices, AI, that are nearby commuting matrices, and they're bounded in norm, then AI are something almost commuting. So they're nearby commuting matrices, then you can calculate their commutators, and their commutators are small. So being nearly commuting means that AI prime minus AI bounded by epsilon. Being almost commuting, this over here will be our delta, is that AI AJ is bounded by delta. And delta is some expression here. So So what we get is nearly commuting implies almost commuting. So let's look at what the proof is. The proof is pretty straightforward. So suppose that there are commuting matrices AI prime, so that AI prime minus AI in norm is bounded by epsilon. So what you can do is you can calculate the distance here, where you have primes and no primes. So what you do is you do that standard kind of trick that you learn in a basic analysis course like Theorem, is that you have these terms here, and you insert two terms with a plus or minus. So you're basically adding 0. And in order to get from one to the other, you want to put one in with one prime and one without a prime. So it's AI AJ prime versus AI prime AJ prime. So these are both the same. So now what we do is we group them. So we take these two and we group them, and we take these two and group them. We apply the triangle inequality. So this is AI prime AJ prime, AI AJ prime. So there's an AJ prime on both sides. So we have AJ prime, AI prime, AI. That's this. This term, the AI, is on the left side, and they're both the same, so we can factor that out. And there's AJ prime, AJ. So AJ prime, AJ, and then AI. So with this part, we've just used the triangle inequality and distributive property. Note that because these are matrices and matrices don't commute, you can't just write this product in any order that you like. However, the inequality will still be true, but I mean, maybe. It will be when we get down to this stage. But at this part, we can't just necessarily mess the order up of the product. Now what we're going to do is use the property that AB is bounded by AB. So the norm of this times the norm of this, the norm of this times the norm of this. Now we know what this is. It's bounded by epsilon. This is bounded by M. This is bounded by epsilon. And then we have to bound this thing. So this is AJ prime. So we know that AI is bounded by M. And we might say, oh, that this thing also is bounded by M. However, that's not exactly true. What you can do is you can show that AJ prime, you just use the same kind of trick again. So AJ prime minus AJ plus norm of AJ. Now this distance is going to be bounded by epsilon. This distance is going to be bounded by M. So basically, I have something that is in the sphere of radius M, and I have something that's epsilon away, then it's in the sphere of radius epsilon plus M. I mean, the ball, not the sphere. So this right here is going to be bounded by epsilon plus M. So altogether, I get M epsilon, M epsilon, so that's 2M epsilon, and then there's an epsilon squared. So that's this estimate here. So if we have the estimate for the commutator, well, the norm of the commutator is this, and then I can subtract 0 because this thing equals 0. And then what we need to do is do this product here. So AI, AJ, AI prime, AJ prime, that's this. And then AJ, AI, AJ prime, AI prime, that's this. Use the triangle inequality, and then we apply this estimate here that we had done to both of these terms separately. So it's just twice this. So 2M epsilon plus 2 epsilon squared. So what we showed is that being epsilon near the commuting and bounded in norm gives us this estimate here. One thing to note is that epsilon here, suppose that we have M is fixed. I don't know, M equals 1 or just a fixed number. And then we're considering epsilon going to 0. Thinking about it asymptotically, this thing right here, epsilon squared, is negligible. So this term is just order of epsilon. So these have the same estimate as epsilon is going to 0. And epsilon going to infinity, then this epsilon squared kind of becomes non-trivial. But as epsilon going to 0, you see that they have asymptotically the same behavior. Again, we showed that being near the commuting implies almost commuting, and the rest of the talk is basically about the converse. So how can you know whether or not almost commuting implies near the commuting? So near the commuting, being nearby commuting matrices, implies that the matrices are almost commuting, the commutators are small. We also showed that the bilinear map, the commutator here, it's a bilinear map. We showed that it's continuous on bounded sets. So if we had AB, A prime, B prime, and we know the norms of all these matrices are bounded by M, what we showed, the calculation we had just done above, is that the distance between the commutator of A prime, B prime, and the commutator of A and B is bounded by 2M, A prime minus A, B prime minus B. And it's the same estimate we had just done above. So the idea is that from this, if A prime and A are close and B prime and B are close, then these commutators are going to be close, up to this bound estimate here. So the problem, which is the converse of the result we just proved, which is that nearly commuting implies almost commuting. The question is, if you have almost commuting matrices, are they nearly commuting? So if their converse, if their commutator is small, does that imply that there exists A prime, B prime exactly commute for A prime minus A, B prime minus B? Both of these are close to 0. So it's kind of an approximation problem. So you have A and B that almost satisfy this equation, and you want to do is find a nearby solution. And because this problem is a nonlinear problem, it makes it rather difficult. If you're just having matrices, you might, like, an inclination is to do some kind of linearization. However, linearization doesn't quite work if you have a nonlinear problem. So it depends. But for this case, it doesn't work. At least not straightforwardly. Anyway, so we're going to formulate this problem here in terms of basically expressing it this way. So suppose that we're going to define some function, epsilon delta, and we're going to want it to go to 0 as delta goes to 0. So epsilon is going to 0. Whenever delta is going to 0, it implies that. And then what we're going to do is formulate this as this. Suppose that the norm of the commutator is less than delta, so it's small. Then it shows that there exists commuting matrices where the distance between the original matrices and the commuting matrices are all bounded by epsilon. And then epsilon going to 0 as delta going to 0 as well. That's what we have up here. So the following theorem is kind of a first step for showing this kind of example. Suppose we have M and N. We'll say what these things are in a second. Then there exists some epsilon, which depends on delta, which is the thing that we wanted. It also depends on some extra parameters, N, M, and capital M. We'll say what these are in a second. So that if we have some collection of matrices, A1 to AM, which are all n by n matrices, and are bounded in norm, and they're almost commuting, then the delta almost commuting, then they are epsilon of delta nearly commuting. So this is the result, the one that we wanted, which is that the commutators are small, implies that there exist nearby commuting matrices. However, one of the assumptions is that how nearby will depend on not just how almost commuting they are, it will depend on the number of matrices here, it will depend on the size of the matrices here, and it will depend on the norm, the size of each matrix that were considered. That's this. So in a paper where I think it's the first time a result like this is stated, at least for the operator norm. The way it's stated for the operator norm, person attributes it to Halmos, and the proof that is given involves a different approach than what we're going to be talking about. I like this approach, not just because I'm familiar with it and it's in the notes for my advisor he wrote on this topic. However, it's also nice because it has a sequence approach. We're going to be using a compactness proof, but it has a sequence approach which has generalizations that we'll talk about later. So let's just see that. Oh, we'll also do the proof just for m equals 2. So we'll do it for 2 matrices. The reason I'm going to only do it for 2 matrices is basically because you have A1 to M. So there's some indices here. What we're going to do is make a sequence of matrices for each of these matrices. So we're going to have 2 indices floating around, and that can get confusing. So what we're going to do is just assume that m equals 2. We're going to have A and B, where their commutators, for instance, are going to be bounded like this. And then we're going to want nearby commuting matrices. So instead of AI prime, so AI would be near AI prime, we're going to have A being near A prime and B being near B prime. So we'll just go into the proof. We'll do it for m equals 2. Suppose not. So suppose that this theorem isn't true. Then you just negate it and then you go through. This is kind of a standard analysis approach to what we're going to be saying. What you can show is that there exists an epsilon, a certain epsilon, not a function, just an epsilon, a number. There is an m and an n, because epsilon is this estimate over here, depends on n and m, but also the number of matrices, which is 2 in this case. M and n, so that you have a sequence of matrices, A alpha, B alpha, belonging to this matrix algebra here, where all the matrices are bounded in norm, like we assume. Their commutators are going to 0, so delta is going to 0. But the distance between A prime and A alpha, so these A alphas and the B alphas, are far away from any commuting pair A prime and B prime. So we're assuming the commutators are going to 0, but then these distances are bounded by epsilon. The reason why we have the maximum here is just to make sure that both of these are bounded away from epsilon. It isn't useful to just say one matrix is close to a commuting A prime, but the other one isn't, because you could just pick one of the matrices to be 0 and then they automatically commute. So you want both of the matrices, A alpha and B alpha, to be close or far in this example, because we're doing a contradiction, so we have them far away. So what we do is we have this sequence, and what we're going to do is use the compactness to get a pair of commuting matrices, which will contradict this condition here, star. So by compactness, because these matrices here, where is it? Oh, I need the alphas here. A alpha and B alpha are bounded by M. They're just some sequence in this matrix space. This is a finite dimensional space, and which is some norm, and all norms are equivalent. So having the ball in some finite dimensional space implies that you have compactness. So you can just find a convergence subsequence. So we'll just label them by A beta and B beta. So these are going to be a convergent subsequence. We'll converge some matrix here, A prime. This will converge some other matrix, B prime, and we're going to show that these two matrices are commuting. So how do we do that? Well, we're going to use the continuity of the commutator to show that because A prime converges to A beta converges to A prime and B beta converges to B prime, then their commutator converges to the commutator of those two things. That's just by the continuity of the bracket. Using the continuity of the norm, you just take norm both sides, and then it's still true. So this is the norm of this thing is converging to the norm of this thing. Now, by assumption, our commutators are converging to 0. So a subsequence will then converge to 0. So that means, because it's converging to these two things, that means that this thing equals this thing in norm. Now, because it's a norm, what that means is that commutator is 0. So we have A beta is converging to A prime, and B beta is converging to B prime, and they commute. And that gives us a contradiction. It contradicts star, it contradicts this assumption here. And why does it contradict this assumption? Well, the reason is that if you have a subsequence converging to it, that means eventually, for some large enough alpha, this thing will be very, very small, smaller than epsilon, and so will this thing, for where you choose alpha equals beta, where beta is large because of the convergence. Both of these will be less than epsilon, which contradicts this. So that contradicts our assumption. So that's the idea. The idea is that we use proof by contradiction to get a sequence of matrices. Then we use these sequences of matrices to then cook up a commuting pair of matrices, and then use those commuting matrices to contradict your assumption. And the reason why I wanted to mention that specifically is because we're going to do an example of a proof like that That's not exactly a compactness argument. Okay, so to just continue commenting on the result we just made, the compactness argument that we gave provides no estimate for this right here, this epsilon, in terms of asymptotic dependence or any kind of dependence in particular. All that we showed was that this thing goes to 0 as delta goes to 0. If we knew, for instance, I mean, if someone just were somehow able to tell you that it was like, I don't know, something like this, a constant times delta to the 1/2, it would tell you nothing about what the constant is. You don't even know it has this form. The point is you just don't know anything about it besides this. Just some function decreasing to 0. So you don't have asymptotic dependence, would be some kind of power law like this example with the explicit exponent. And even if you had that, you wouldn't know what the constant is. It also doesn't provide any information on whether epsilon necessarily depends on n. So we had in the assumption that epsilon depended on, let me get the order right. Doesn't really matter, but okay. So delta n, m, and capital M. So it depends on the size of the matrices, it depends on the number of matrices, and it depends on the norm of the matrices. So kind of naturally expected to depend on the norm. Not entirely true. I mean, we do expect it a lot of times. Number of matrices, well, that's kind of like a natural assumption to assume it depends on the number of matrices. Depend on the size of the matrices, well, maybe. Again, you might, unless you've studied the problem a lot, you might not know whether or not you can remove any of these conditions. For us particularly, we don't want it to depend on the size of the matrix. One reason that we might not be interested in is basically related to where this problem came from. Or you can see an early development of it, and then you can say where the applications are, and so that's one example. So let's make an example. So von Neumann, in a paper, he was talking about how if you have commuting observables, I'm just going to formulate it this way. This is motivated by something that von Neumann was talking about. So basically, what you do is if you look at classical versus quantum statistical mechanics, so maybe what you often do is that you take this thing called phase space. So you have some coordinates x and p or something. And what you do is, so this is the positions and these are the momentum. And what you do is you can just partition that up. And then for each little cell here, you can say things about it. And the idea is that you can do this partitioning of values here, x and p. For quantum mechanics, if you have the observable, the position, and the momentum observable, or if you're doing some other variables like spin or something like that, you can't do this thing where you're partitioning things. The idea is that observables that don't commute, like the position observable or the momentum observable, because they don't commute, you can't do this kind of partitioning. This is a Heisenberg uncertainty principle. So basically, if you know that you can localize in one variable, then the other variable is necessarily not localized. So you can't do this kind of partitioning like that. However, if you have observables, operators, where they commute, then what you can do is you can kind of do this kind of thing. So this is the kind of question that you might be thinking about, which is, suppose that you take some observables, A prime and B prime, for some macroscopic system. So, I mean, for instance, maybe you have some blob of thing made of particles. And you're measuring something, not just a particular value of some kind of element here, but also it's like a total sum, basically. So what we're used to for macroscopic things is being able to measure things in a way that don't behave quantum mechanically. They behave classically. So we're used to being able to know whether or not an observable has a certain value. And for another thing, we're also used to being able to measure them simultaneously. You can't do that in quantum mechanics like you can do it in classical mechanics. So we might expect some kind of relationship to happen when you're looking at quantum mechanics and for classical mechanics when the systems are very large, because we expect quantum mechanics to approximate the classical picture when you have large systems. So the idea is that although these observables here, they might not commute, but because they represent macroscopic systems, we expect their commutator to be small. We expect them to almost commute. And even though we can't exactly measure them, maybe you can measure nearby commuting observables So maybe you can find nearby commuting observables, A prime, B prime. Remember, the hat just means operator. So that they almost represent the thing that you're measuring, like in some kind of abstract sense. And they might actually be, so this is von Neumann's idea, that when you're actually measuring these macroscopic systems, and you're measuring these different things, you think you're measuring this, but maybe you're not actually measuring them. Maybe you're measuring nearby commuting things. And then once you're actually measuring these nearby commuting things, you can then do these kinds of things where you're doing partitioning and stuff like that. The things that you do classical mechanics. So that's kind of like a motivation for the problem. So what does it have to do with dependence of epsilon and m? Well, suppose that you know the commutator of A and B in norm is, I don't know, like 60 h bar or something. So a pretty small number. What you want to then say is that these things, the A hat is approximately A hat prime, and B hat is approximately B hat prime. And you want how nearby they are to be small, because this is small. However, what can happen is if it depends on the size of the matrices, then you can easily run into problems. Because, for instance, suppose that the system here has size, I don't know, 10 to the 30 or something. Some kind of large system of particles. And maybe, as matrices, maybe they're 10 to the 30 by 10 to the 30 matrices. And you know that their commutator is only this small. So what might you expect? If the epsilon depends on n, so maybe epsilon is, I don't know, some number times delta to, I don't know, 1/5 or something. For when delta, where the norms here are bounded by 1 or something. Is delta going to 0? If this thing is very small, then you can see this. However, if there's also a dependence on n in some way, like, I don't know, multiplied by n or something like that, then I'm just kind of roughly sketching it out. Then you would have a 10 to the 30 here. 10 to the 30 times this basically h bar to the 1/5. So you're basically comparing 10 to the 30 to the 5th versus h bar. And what you can easily see is that if the size of the matrices get very large, even if you have a commutator that's very small, you can run into some problems pretty quickly. So you basically might not be able to get epsilon to be actually very small, even though you expect it to be small. So that's kind of the idea. It's just very rough sketch. It's not the formulation of an actual problem. However, there are, because of this h bar example, the idea is that you can also, there are problems where you can formulate it mathematically. However, I'm just doing it kind of vaguely because that's the idea that von Neumann was giving, and that also justifies a reason why you might be looking for matrices that don't depend, estimates that don't depend on the size of the matrices. So now we're going to continue with some key results in the topic that we're looking at. So not only are we going to be looking at almost commuting matrices, where AI, where the epsilon just depends on delta, maybe it depends on the norm of the matrices. It probably depends on m. We'll only focus on m equals 2. We'll see that m equals 2 is the interesting case, at least for the results that we're going to be going over here. We're also going to be focusing primarily on the case where, for this problem, almost commuting near the commuting matrix problem, where the matrices that we're looking at, the AI almost commuting matrices, and the nearby commuting matrices, the approximates of them that actually commute, we're going to assume that all of them are self-adjoint, or just meaning Hermitian. So A star equals A. And a reason why you might be looking at that is to say that, well, binomials example, we're looking at operators. Hilbert space operators are modeled by self-adjoint matrices in finite dimensional systems. So you would then say, well, self-adjoint matrices are the fundamental example to be looking at. However, self-adjoint is also a nice thing to be looking at. Not just because we have some kind of extra condition, but also because they're self-adjoint. You can do spectral theory with them. That's the key idea. So that self-adjoint things, operators that are normal, you can do spectral theory, and it makes it a lot more useful to have some kind of extra nice condition like this, because you can do things that you just can't do with non-normal matrices. So this is so now we're going to give an example. So and it's an example theorem. Choi calls it an example theorem, which is basically an example, but it's a key example. Suppose that we have these matrices. We have A, which is some diagonal matrix here, A1 to AN. Now A1 is going to be around -1, AN is around 1. I mean AN, and A1 is around -1, and then A2 is A1 plus H. A3 is A2 plus H, etc., etc. So basically nicely spaced entries, diagonal matrix entries. And B is going to be upper diagonal weighted shift. And the entries here are starting off near 0, going up to around 1, and then going back down on some kind of semicircle. Now, what you can show you the operator norm is, because this matrix is diagonal here, then the operator norm is just the maximum absolute value of these entries, which we said basically we're going to get bounded by 1. B, because this matrix is off diagonal, but there's only one entry in each in each column, then the operator norm is the maximum absolute value of those entries. And so we said that all of these are bounded by 1, so the operator norm is bounded by 1 as well. You can show that the commutator of A and B is bounded by 2 over n. So the 1 over n basically would be the idea of what the spacing is, the spacing between these entries here. These are all distinct, but there's spacing 1 over n basically. So what you can show is that the commutator of A and B is going to be bounded by some estimate like that. So the commutator is going to 0. An idea for where you can see this is, suppose that A and B actually commuted. Because this matrix is diagonal matrix, that means that A and B would both have to be diagonal. B would have to be diagonal the same form, because these have distinct diagonal entries. So if A and B commuted, then B would also be diagonal. And what that means is that it's taking an eigenspace here. So the eigenvector corresponding to this column would be E1, corresponding to the next column would be E2. B would need to preserve the eigenspaces because it commutes with A. So it would take a vector here, E1, and it would send it to a multiple of it. However, kind of an idea for how it could be almost commuting, but not actually commute, is what you do is you take an eigenvector here of a certain eigenspace, and you send it to a vector, or actually, you take an eigenvector here of a certain eigenspace. This is eigenvalue A2, and you send it to the eigenspace of a nearby eigenvalue. So that's kind of an idea of how it can almost commute. And you have to be careful about the technicalities of what you mean by these things, and make sure the operator norm actually is small for the commutator. But that's the idea, is that in this thing here, what this entry here means is that BE2 equals B1 E1. That's what this means when you have upper diagonal. It takes E2 and it shifts it backward to E1, but with a scaling of B1. So in general, BEN is Bn minus 1, En minus 1. So it's taking the En, the vector that belongs to the An eigenspace of A, and it's sending it to the An minus 1 eigenspace of A. And it's also scaling it by this Bn here. Now the idea is that because this thing is bounded by 1, and these are nearby eigenspaces, the eigenspace eigenvalues are nearby, basically 1 over n distance. So you can show that the commutator is bounded by 2 over n. But that's the idea of the proof. But you have to be, if you're going to do this kind of thing, you have to be familiar with how to calculate the commutator and then calculate the norm of the commutator and then make sure that it's small. However, that's the main idea. So we have that they're bounded in norm by 1, their commutators are small, and as you send n to infinity, this is going to be going to 0. However, what you can show is that the distance, what Choi showed, is that the distance between A prime and B prime and B for any commuting prime, any commuting pair A prime and B prime is bounded below by some function here, which is not converging to 0. So this is going to 0, but this is not converging to 0. Basically, it's converging to 1. So this is the example. This does not violate what we showed earlier in terms of the compactness proof, because the matrices are growing in size. So these matrices here, A1 to AN, as n is going to infinity, A and B are both M and M of C. And as you have n going to infinity, you can see the matrices are growing in size. So even though the norm of the commutators are going to 0, the distances between A and A, the distance between these pairs of matrices and our commuting pairs are actually still staying away from 0. So Choi's example here doesn't violate the thing that we've gone over in terms of compactness because they're growing in size. However, it does violate the thing that we would want, which is here we have almost commuting matrices that are not nearly commuting because they're far away from commuting matrices. Using, do I want to say how? Yeah. So one idea for how this is proved is, I just make a quick comment, and is that what you can do is you can package these two matrices in terms of a block matrix. You have A minus A, and then you have B and B star, the adjoint. You make this block matrix. And so what you can show is that this block matrix here, this matrix here is Hermitian, it's self-adjoint. So what you can show is that its eigenvalues only come up in different parts of the complex plane. So this is the complex plane here. It's Hermitian, so the eigenvalues are on the real line. The eigenvalues turn out to only be centered around -1 and 1. They're kind of nearby there. So they can only live in this little area for these particular matrices that we have. However, what you would need to show, so if these matrices commute, it turns out that the number of eigenvalues in here, in this little area near -1, needs to be the same number as the eigenvalues over here. However, for these particular matrices, it turns out because there's like a shifting going on here, where it's shifting the eigenspaces, you get some kind of index problem, where basically the number of eigenvalues on one side is not the same as the number of eigenvalues on the other side for this kind of matrix. However, let me just erase this. However, if A and B are nearby this commuting matrices, then these block matrices are nearby. And if you have two self-adjoint matrices that are nearby, then their eigenvalues are going to be nearby each other. So if you had this matrix here with, if this matrix here was nearby commuting matrix, nearby a block matrix made of commuting matrices, then what you would know is that the number of eigenvalues here, if you just move them around a little bit, you move them around in here, then you get the same eigenvalues for this thing. However, if you just look on one side and you say the number of eigenvalues over here is more than the eigenvalues over here, the only way that you can perturb this to get this is to take one of these eigenvalues on one side, if there's more on the side, and move some of them over. And basically, you can't do that. You see this distance here, you can't just move it over without getting a large perturbation, which is where this kind of estimate comes from. It comes from an index consideration. And this kind of index idea has been generalized, and it's a topic people are still working on nowadays. But this kind of key idea back in the 80s was a key starting point for this kind of index thing, it seems. So what you can do is that if you're looking at these kind of matrices that are not commuting, you can think about kind of examples like this, and they're kind of important. However, A is self-adjoint, and B is not self-adjoint. However, if you have these two matrices that are, this one's self-adjoint, this one's not self-adjoint, Davidson already has an example where he goes over some examples like this. So basically, if he has an example proof, basically, if you have A and B, where A is a normal matrix, I mean, A is self-adjoint, and B is a almost normal matrix, kind of like a matrix like this. If you were able to then find commuting matrices A prime and B prime, so Choi's theorem is actually pretty interesting because it shows that there are no nearby commuting matrices at all. It doesn't assume any self-adjointness or anything like that. Davidson showed that if you had A and B, and this is almost normal, you could then take B and break it up as the real part, the imaginary part. And if B is almost normal, what I mean by that basically is that the real parts, the imaginary parts almost commute. And these things almost commute with A. So then you have A, you have the real part of B, you have the imaginary part of B. If you have three matrices that are almost commuting, if they converge to actually commuting matrices, then what you could do is package them back to you can say B prime is R prime plus I prime. And then what you'd have is B prime, because these things commute, this thing would commute. If these things were also self-adjoint, then B prime would be normal. This thing would be commuting, and you get this. These things would be nearby commuting matrices. That's the idea. So basically, using examples like this for two almost commuting matrices, one of them's self-adjoint, one of them's almost normal, you can show that if you have A1, A2, A3, which are self-adjoint and almost commuting, it is not the case that they're nearly commuting. So that makes the problem interesting because we said it earlier with binomial's example, we kind of expect almost commuting matrices to be nearby commuting matrices. However, for three almost commuting matrices that are self-adjoint, you don't have that result for the nearby commuting matrices that are almost commuting. Sorry, I don't know why I wrote that. That are self-adjoint. Those are the ones we're interested in anyway. However, Lin in 97 showed the following result. So this is when the paper was published. So basically was that if you have n by n matrices, n by n matrices that are self-adjoint, they're bounded and normed by 1. Then there exists commuting matrices A prime, B prime. So the thing that we wanted is true. So the distance between these matrices is bounded by epsilon delta, and epsilon delta is going to 0 as delta goes to 0. And the key result is that this epsilon of delta doesn't depend on n. Based off how the thing is formulated, we have the norms are bounded by 1, which means you know that if you rescale things, then it does depend on the size of the matrices. The absolute value matrices, you see that it depends on them. However, it doesn't depend on the size of the matrices. Obviously it depends on the number of matrices because these are only just two matrices. Again, we showed three matrices, just doesn't work. However, Lin showed that two matrices does work. So the original proof was pretty technical. Friis and Rordam published a simplified version of the proof. The publication date is actually before this date, and not entirely sure the reason for that. If I were to just speculate, it would be because this proof is much simpler and it was easier to get out, even though this paper had already been circulating as a preprint, which this paper refers to. So we're going to go over the Friis and Rordam paper proof, and the idea is to but we'll go over the proof. But one thing I wanted to mention about the proof is that it has been generalized. People still applying it for other types of matrices and other examples and such. So it is a good, it's kind of like the reason why we're going over it is because it's a foundational argument to prove this foundational result. However, it's also foundational in the sense that it's been generalized in a lot of different ways to other problems. So we'll go over the proof idea. So suppose that this theorem, this Lin's theorem up here, isn't true. What kind of thing could you do with that? Well, you just do the same kind of thing we had done with the compactness. What you do is that there is some kind of epsilon, and you have some sequence of matrices where their commutators are going to 0, but the distance between the sequence and any commuting pair, A prime and B prime, is bounded above by epsilon. However, there is a key distinction between this and the thing we had mentioned before. So first of all, I didn't write it, but it's true that both these have bounded norm. They're both bounded in norm by 1. We're just assuming that. But also, the size of the matrices is allowed to depend on alpha. So basically, the size of the matrices are able to change. So this is where the compactness will completely fail, because these matrices, first of all, they're different spaces. Even if you think of matrix spaces like 2x2 matrices somehow sitting inside 3x3 matrices, which you can do. You can do, if you have a 2x2 matrix here, A, B, C, D, you can embed it into A, B, C, D, where you just put zeros everywhere else. So you can think of 2x2 matrices sitting inside 3x3 matrices. However, if n alpha, the size of the matrices is allowed to grow, then you don't get any kind of compactness, because you're just wandering through a larger and larger space of matrices. It's growing. The size of the matrices, anyway. So you can't just do some kind of compactness. You're not going to be able to find a convergence subsequence or something. However, the same idea of trying to find something where you get commuting behavior and then using that to get a contradiction, that's the same idea still. So this is the contradiction part of the proof. This is the approach. Now what we're going to do is we're actually going to reformulate. And the reformulation, I think, you can reformulate before you do the proof, but I'm just trying to go through the proof. So of the problem as stated in terms of almost commuting self-adjoint matrices. You can also state it in terms of almost normal matrices, which we're going to do. So basically, if you have A alpha and B alpha, these are almost commuting real matrices. You can do is you can form N alpha to be A alpha plus I B alpha. So basically, A alpha is the real part, B alpha is the imaginary part. And it turns out that because A alpha and B alpha almost commute, then this N alpha is almost normal. So just remember is that if A alpha and B alpha were actually commuting and self-adjoint, if you made this thing here, then N alpha would satisfy this. N alpha and N alpha star would commute. Basically, it would be normal. You could just check that. However, because these things almost commute, it turns out that N alpha is almost normal, which means the commutator of N alpha star and N alpha is converging to 0 in norm. So this is the thing that we've gotten. And from this assumption up here that it's distance away from any commuting self-adjoint matrices, it implies a result like this, that N alpha is almost commuting as alpha is going to infinity. However, it's distance away from any normal matrix. So what we're going to do is we're going to take this reformulation. We have some sequence N1, N2, N3, which we're going to call N alpha, which we will then call just N. So this is some sequence of matrices, and as you go farther and farther down the sequence, they're becoming more and more closer to being, they're becoming such that they look like they're becoming more normal because their commutator of them and their N star, and their adjoint is converging to 0. However, no matrix in here is going to be actually normal. So what we're going to do is, instead of taking a limit, because we can't take a limit because things aren't converging, what we're going to do is we're going to consider this whole thing as an object in and of itself. So in some sense, we're going to get some kind of convergence, but it's not really like convergence. We're going to consider this following C-star algebra. So the C-star algebra is what we do is we think of each matrix algebra here. These are all matrix algebras. And as I said earlier, they are all C-star algebras. So what you can do is you can form a new C-star algebra, which is going to be the direct sum of all of these things here. Basically, it's a sequence space. Space of sequences of matrices, where this matrix is from here, this matrix is from here, et cetera, et cetera. And we're going to define the norm of this to be the supremum. Now, you should think of this as an analog of L infinity of n. It's a non-commutative version of it. So, this right here is the sequence of all bounded, is the set of all bounded sequences. And this is the set of bounded sequences of matrices. But so like this would be Z1, Z2, Z3, where the sup of the absolute value of Zi, or let's say Zn, is equal, if we call this whole thing Z, then it's just the norm of Z. It's the supremum. However, this would be L infinity of n. And we're doing like a non-commutative analog. So it's the set of sequences that are bounded. Now what we're going to do is we're going to find J to be the following closed ideal formed by all of these elements here, but they're not just going to be bounded, they're also going to converge to 0 as alpha goes to infinity. So this right here is the analog of what they call C0 of n, which is the subspace of all sequences here where these Zn's converge to 0. So they're bounded sequences that converge to 0. And it is an ideal, so J is an ideal, meaning that if you take any sequence here and you multiply it by some other sequence, so C alpha, and you multiply by some other sequence D alpha, C D alpha, the product here is entry-wise. If C alpha is converging to 0 and D alpha is bounded, so this thing is in J and this thing is in A, then when you do the product, well, this is bounded, this is converging to 0, so the whole thing is going to 0, so this thing is in J as well. So basically, if you take the product of things in J and A, you do product on one side or the other side, then you get something in J. It's a closed two-sided ideal. It's a two-sided ideal. This is the ideal property, but it's also a subspace. So as far as a ring is concerned, this thing is like a ring. If you think of it in terms of abstract algebra, this thing is an ideal. It's closed, and you can show that it's closed in this norm here, the sup norm. So because we're dealing with C-star algebras, basically Banach spaces, if you have subspaces and such, you want them to be closed subspaces. So you can, well, I mean, sometimes you have things that aren't closed, but if they're closed, it's nicer. And how is it nicer? It's nicer because if you have a ring, just in general, you could form a quotient space. I mean a quotient. If they're like vector spaces, then you could form a quotient space. If they're Banach algebra, if it's a Banach space, a Banach algebra, or something like that, C-star algebra, you can also form quotients. However, you want things to be closed when you're quotienting so that you get something that's nice. So you also get something that has a nice norm. So we're going to formulate this thing with the almost commuting matrices in terms of that. So we have some sequence here of n1, n2, etc., etc., some sequence n alpha, which we'll call n. And we know that although these things aren't going to 0, we know that they're all bounded. All these are bounded by 1. So the norm of n is bounded by 1. And we know the commutators of n alpha and alpha star is going to 0. So what does that tell you? We know this thing is going to 0 as A is going to infinity, alpha is going to infinity. And that's exactly this condition here. That means that n alpha star n alpha, if you think of this as a sequence, then you can call that the commutator of n star with n, and this thing belongs to J. So basically, this sequence space here, the sequence of all commutators, is 0 mod J, because it belongs to J. So what you can do is you can consider this thing I mentioned earlier, which is this quotient. You take A and you form P, it's a projection, I mean pi, I guess, and you map it to A mod J. So if you have any sequence here in the sequence space, you can map it to C mod J. So in some sense, this is actually kind of giving you a limit because we have some bounded sequence, and you're modding through by the space that of all sequences that are converging to 0. So if you have a sequence here, which is converging to something, and you have another sequence that's converging to the same thing, then they're going to be the same in the quotient. So in some sense, it's kind of like a limit, but it's not entirely a limit. Anyway, so we have this projection here. And what's so nice about the projection? First of all, it's a projection. So this is a Banach space. Because this is a closed subspace, you can do this kind of quotient and you get a nice kind of map. However, because this is a C-star algebra, and this right here is a closed ideal, you also, it's not just a closed ideal, but it's also closed under the star. If you take any element, if you take a star of the thing in there, it's also in here. You know, some kind of technical conditions like that. More abstract nonsense. What happens is that if you do this map right here, it turns out to respect the C-star algebra properties. So this right here is going to be C-star algebra. This will be a C-star algebra. And then pi will respect the C-star algebra properties of these two spaces. You're going to get a homomorphism, which will respect the star. So if you have pi of some sequence n alpha, and you do star of that, then you can just take the star right out. But also it will respect the other operations, just like a normal ring homomorphism. And this is just a projection onto the C mod J. And remember, this right here is an equivalence class, the equivalence class of all. If you have two equal equivalence classes, then it just means that C minus D belongs to J. And not only that, so we have this space. I mean, why did we even consider this? The reason is that this thing, this sequence belongs to J. So even though the commutator isn't 0, the sequence commutators belongs to J. So if you mod through by J, you get 0. So the idea is that pi of n is in this C-star algebra is actually normal. And you can check that by just calculating the commutator of pi of n star and pi of n. Because pi respects the star and it respects all the properties, the C-star algebra properties, you can then pull pi out. You get pi of the bracket here. And then this bracket here belongs to J. So the bracket belongs to J. So pi of something in J is 0 by definition, because it's modding through by J. So pi of n in some abstract C-star algebra is normal. So as a summary, we have these almost normal matrices. It's a sequence of almost normal matrices in some larger and larger matrix spaces. We package these matrix spaces into this matrix sequence space, C-star algebra. We package n alpha sequence as a matrix in this sequence space. This is an almost normal matrix. At least by almost normal here, I mean, it's not an almost normal matrix. What I mean by almost normal is that, you know, if I throw away the first 50 elements and I form a new sequence, then I can make the commutator of n star and n as small as I like. I can make this as small as I like and still essentially have the same problem. It's almost normal, in particular, when you're looking farther and farther as alpha going to infinity. And how that turns out when you do the mod J, when you do this projection down, is that you do a mod J down here. When you project it down, you get pi of n, and this thing is actually normal. So our goal is to get a contradiction. I mean, it's a proof by contradiction. Is to take this normal matrix here, I mean, normal element of the C-star algebra here, and lift it up here to a normal thing. So let's talk about that in some detail. So basically, we have n here. It projects down to pi of n. This thing is normal down here. This by being projected down, what we mean is that this thing, quote unquote, lifts to this thing up here, meaning that there is something that projects down to it. However, this thing up here is not normal. What I want is a normal matrix n alpha. I want one of my n alpha to be nearby a normal matrix. So I want this thing to be small. Smaller than the epsilon, which I assumed that it wasn't less than epsilon. That was the assumption. Remember, we started with this where it was smaller than, bigger than or equal to epsilon for all alpha. So I want this to be true in order to get a contradiction. So what you do is you take pi of n, you do some kind of perturbation to get a normal element here. Then what you do is that you assume that this thing it lifts to some n prime up here. Now this thing is normal. This thing is also normal. This thing normal does not lift to a normal thing. However, this special a, which is normal, will lift to a normal thing. And if we assume that this distance down here is small, so if pi of n minus a in this quotient space norm is small, then that means that the things that they lift to, n minus n prime, now these things won't necessarily be small. However, when you're taking, because they're sequences, if you take their sequence as alpha going to infinity, this is going to be small. Because this is small. That's just what it means to be in, this is what this means to be small. And if this thing is small as alpha is going to infinity, that contradicts this. I mean, that will show this, which contradicts the fact that this is the assumption that we need to contradict. If this thing is going to 0, or it's at least small as alpha is going to infinity, then it contradicts this as long as it's smaller than epsilon. So that is the idea. We want to lift pi of n. We can't exactly lift it. We lift something nearby it to some normal n prime, where this distance here is small in the a mod j norm. And how exactly are we going to do this? Well, the idea is to use this thing called functional calculus for C-star algebras. So because pi of n is a normal element of the C-star algebra, you can do this thing called functional calculus. And it's kind of related to the thing that we were talking about earlier with a normal matrix and how you calculate its norm using its eigenvalues. Suppose that we have pi of n. What you can do is, given any function, so pi of n, because it's a normal element in the C-star algebra, has this spectrum. This is going to be some compact set. If you take any continuous function on that spectrum of the normal matrix, you can define a continuous function on this compact set. You can define a continuous function f of my normal element. And then in a very natural way. So it will respect all kinds of, it'll behave the way that you want it to behave when you say functions of elements. And not only that, but the norm of this function of the normal element is going to be the supremum of f of lambda, where lambda are all the elements of the spectrum here. So just as an analog, remember we had a, if this was normal, then the norm of a is the supremum, which is actually a maximum because it's a normal matrix that has a finite spectrum. So you have lambda in the spectrum, absolute value of lambda. So this is true for any normal element of a C-star algebra. So you have the norm is equal to the maximum absolute value of anything in the spectrum. However, when we define this functional calculus, it turns out to be true even if we apply a function of it. So function of a, norm, is the supremum of the function of the lambda, the function of the eigenvalues, or not just eigenvalues, but anything in the spectrum, lambda and sigma of a. In general, eigenvalues aren't things that you really have for a general C-star algebra. Not just because the C-star algebra aren't operators in general. You could think of them as operators, but they're not really operators, like how you find them. So it's not directly obvious where the eigenvalues come from. And in general, even if you have an operator, I mean, even if you have a C-star algebra you're thinking of as operators, they might not actually have eigenvalues. So this kind of operator here, you just apply a is sigma of, I mean, a is pi of n. So that's what this thing is here. So you have this kind of nice thing. You can define functions of the normal element. And when you're thinking of a function of a normal element, you're actually thinking of the function, you're kind of thinking of it almost as just the function on the spectrum. The spectrum is just some compact set in C. So it gives you a nice way of relating functions of normal elements to just functions on C, just normal functions that you're very familiar with. So it gives you a nice way of dealing with all kinds of stuff. So so why did we go off in the digression? The point is that that's partly why we like the normal matrices. the normal element of the C-star algebra. So, let's continue on with our idea. So remember we were talking about this lifting thing, this whole idea of liftings. So what we can show is that if you have elements A in your quotient here with a discrete spectrum, then it can be lifted. So if you have A here, and you take the spectrum of A, in general, it's going to be some compact set in R and in C, I mean. So compact subset of the complex numbers. And, it can be any kind of compact set. It could be like a disk, it can be all kinds of stuff. However, if it's a discrete set, meaning, it's just a discrete subset of complex numbers, then you can lift it. So, knowing that, when we have pi of n, and we want to approximate it by an element here that can be lifted, a natural case of thing to lift is to take some pi of n, which will have some kind of spectrum here that's kind of messy, do some kind of perturbation to pi of n in order to make A, which will have a discrete spectrum, and then we'll be able to lift that. So the idea is to take this, using various functional calculus-like stuff, and then do that to find a normal element of our C-star algebra that is nearby pi of n. And this thing will have a discrete spectrum, so we can then lift it to n prime in A. And that will give us the contradiction that we wanted, or that we said earlier. Because when I said it's nearby, I definitely want it to be less than epsilon, so I can get that contradiction that I wanted. So a natural question you might ask is, how exactly does that work? Well, first of all, it doesn't always work, but let's just mention some of the ideas. So basically, if you have pi of n, because all the n alpha are bounded by 1, pi of n in this new C-star algebra is going to be bounded by 1. So you could think of the spectrum as lying in some large rectangle. I don't know, maybe it is a rectangle. So it's some spectrum in here. This is not discrete in general. So what we do is our first step is that we pop little holes in the spectrum. Now the spectrum might not equal to this. Maybe it's some subset of this. The point is that I can't tell the difference between this and anything else. So if I define a function of pi of n or whatever, I can only really define it on this set here or some compact set in here. And then, yeah, so let's continue here. So what you do is you pop holes in this. So you pop some holes in some kind of lattice, like a little rectangular lattice. And you can do that. It's not that hard, actually. Popping holes isn't that hard. Even if it's a discontinuous thing, so remember we have continuous things, it isn't actually that hard. And basically, popping holes is kind of like making something invertible. So if you have an element here if you're missing a point here on the spectrum, if lambda equals 0 is not in the singular values of, I don't know, some element here, let's call it B. If it's not in the spectrum here, that means that B is invertible. And you can kind of take something that's not invertible and make it invertible by doing some kind of it's not really that hard, actually, to pop a little hole here. And then when you do popping a hole in other spots, it's kind of like what you do is you do B minus lambda, and then you pop a hole in that one by making this thing invertible too. So you can pop holes in things. It's not really that hard. Once you popped holes in it, you can do a homotopy transformation. So this is you can do this. It's not a continuous thing, but you can do it. This is continuous, where what you do is because you popped a hole here, because you popped a hole here, you can then use a homotopy transformation, homotopy equivalence, to then stretch it out so that the spectrum here then goes onto this little rectangle here. So basically now you can make sure that the spectrum of A, which is so we started here with pi of n, and then we're doing successive changes. So here we get an A here, where it's missing these spectrum points here, and then we get another A, which spectrum lies on this grid here. And this is the hardest part, I guess, where you basically need to cut these. So basically make cuts here. So you get little, you're basically cutting out part of the grid. So you get these little crosses or plus signs. By cutting, and in general, cutting is non-continuous, but you also don't want to mess up the thing here. So here, when you're popping holes, you know, maybe you're messing the spectrum nearby or whatever, but you don't really care because you're just assuming that there could be spectrum everywhere else as long as you're not messing with these little holes here. With these things you're cutting, it's actually pretty difficult, and it definitely does use the fact that A here is not made out of just any C-star algebra. It's made out of these matrices. And in general, if you make a certain assumption like that A is a special kind of C-star algebra, then you can do this kind of popping hole thing. That it's real rank 0, which means that self-adjoint elements are approximated by self-adjoint elements with finite spectrum. So anyway, so what you do is that you approximate it by this, and then once you get this is pretty straightforward. You just do homotopy equivalence, and you just continuously shrink these down to a single point along this thing here. So you have a little cross, and then you could take points here and move them in this way. And so you get a little grid of points. And so along the way, you keep making successive changes to this element A, and then you get an A here that has discrete spectrum. And the point is that you can do this to this normal element here, and that's a pretty straightforward way of doing it. And then here's the fact is that you took something with a spectrum in the square, and then we took it to the spectrum here, which is just a discrete set of points. And then as long as the points here are rather close, that's the idea, that you can then make this approximation with a discrete spectrum. And that would be the proof of Lin's theorem, well, the Friis and Rordam version of it. And what you can see from the proof is, first of all, it's kind of like the compactness proof in an abstract sense, because it uses this sequence of counterexamples, and however, it doesn't use a limit. It kind of does in a certain sense, but it's not exactly the same way. And it uses these kind of nice functional calculus maneuvers. And like I said, these kind of proofs are generalized in other contexts. And even the result that we're going to mention down here, of a result that actually does get an estimate, it basically uses a similar kind of argument here, at least for this part. It's using this compactness. It's using this thing where you're popping holes and you're doing this kind of stuff. You can do that in your C-star algebra pi of n. However, the non-constructive part comes from the fact that we assume that we had a sequence of matrices all the way up here, this n alpha. We assume that we had this sequence that was a witness to the fact that the theorem wasn't true. These things are far away. However, the commutators are converging to 0. Then what we do is we package them into into an n. We apply pi of n using the quotient. And all of that came from the assumption, the proof by contradiction assumption. So once we made our proof by contradiction assumption, we then get this normal element pi of n. And then once we get this normal element pi of n, we apply these C-star algebra ideas. Now what you can do is kind of cut out that part, the non-constructive part, which is the proof by contradiction, to get this normal element. And that is the proof that we'll talk about in a second. I mean, we're actually not going to go over the proof, but this result, this proof right here, this result right here, where you have this almost normal matrix, this step from almost normal to normal uses the C-star algebra stuff that we talked about in terms of you draw the grid and the spectrum and you want to pop holes in it and stuff. However, this little stage here where you make the pi of n, what you don't is you don't do pi of n. What you do is you take n and you enlarge it to a normal matrix. So n is not normal. However, what you can do is you can, if you write n as x plus iy, real and imaginary part. Actually, I didn't need to mention that. If you have this normal element here, what you do is you approximate it by a matrix. I'll call it, to not use the notation in the paper, you can call it X. The point is that this right here is a matrix here. And this right here is like, you can think of it as an n by n matrix. What you do is you approximate it by a bigger matrix where this block up here approximate this, but the whole matrix, this whole bigger matrix, is a normal matrix. Now with this normal matrix, you do apply the C-star algebra stuff, and then you hope that once you get your normal matrix here, using the kind of thing where you're popping holes in the spectrum and such, the reason why you do that is so that this normal block up here, you can then show that this thing is going to be approximated by this, but then also from this, you can get a normal matrix. So that's kind of the idea for this proof, but let's actually mention the reason why I have it in these slides here. This approach, so the proof above for Lin's theorem, provides no estimate for this estimate, for this thing, as delta is going to 0. So basically, we know that as delta is going to 0, we have no estimate for how close the nearby commuting matrices are. However, we have this theorem by Kakowski and Safarov, which is 2016, is that there exists a constant c bigger than 0, so that the distance here between any random matrix, maybe almost normal or whatever, to the set of normal matrices is bounded by a constant times the commutator of n star and n to the 1/2 power. For any matrix n in Mn, but then it's also true, it's true that this thing doesn't depend on n at all. You can see it here. It just depends on the commutator, so delta is the 1/2, and a constant, and the constant here is just a fixed constant. It doesn't depend on n at all. And in fact, this also applies, the way that it's proved, it's not proved for C-star algebras. It's proved, the same thing with Lin's theorem, is proved for the real rank 0 C-star algebras. It's not proof for matrices. So this result is it's a very nice result. It's also nice because it is, not just because it gives you a nice estimate here, and the C, you know, the paper doesn't go into what the C is. It's just kind of a constant that's, you know, you do a bunch of calculations and then you say there's a constant here and there's a constant here and there's a constant here, and then you say, you know, along the paper you say we're just accumulating constants, but the constant is never explicitly calculated in the thing because, you know, it'd be kind of annoying to go through and calculate it. But it does give you the optimal asymptotic estimate. This is the estimate here for epsilon of delta, and this is constant times delta to the 1/2. Now, if you call it constant times delta to the gamma, where gamma is 1/2. Why is this optimal asymptotic estimate? Well, first, let's restrict to the case where n is bounded by m in norm. And we're going to see that this is optimal even when you restrict to this by what's called the scaling argument. Suppose you have a matrix n that's not normal. Take a real number between 0 and 1, and we're going to take nr to be r times n. And what we're going to do is we're going to take r conversion to 0. And we're going to see how the inequality scales. Because nr is bounded by m, so we're assuming that n is bounded by m and r is less than 1, we can then apply the inequality to nr, not to n, but to nr. So we have this distance here with nr, and then we have this estimate here, nr. And we just see how both sides scale. Well, the first thing is that the set of normals is not a subspace of matrices. You can't just take a normal matrix and add another normal matrix to it and get a normal matrix. That doesn't always work. However, it is invariant under scaling. So if I take a normal matrix n prime and I scale it to n prime times r or something, then it is also going to be normal. So this set here is scaling invariant, and I scaled this. So what I can do is I can see that this whole thing is the distance from n to the set of normals times r. So it's just a number that depends on n. It's non-zero. It's a non-zero number because n is not normal, times r. So it's an r times a constant. Here on this side, nr has an R here. This is an NR, so there's a factor of R here. There's a factor in R here. When you do the commutator, it's a quadratic operation because you're multiplying and subtracting and multiplying. So this whole thing is scaling as R squared. There's a gamma here, so it's scaling as R to the 2 gamma. There's a C here. When you pull the constant out, you get times n star n times C. So there's a constant here that's a C. There's a constant here from the commutator of n star and n, that's here. And then you have R to the 2 gamma here. So you get this inequality. R is bounded by a constant times R to the 2 gamma. And in order to see when can this inequality be true as R is going to 0, what you do is you can just move this term over here. We get R to the 1 minus 2 gamma is bounded as R is going to 0. So how can this be true? Well, I mean, if you just think of it as an example, this right here is not bounded. As R goes to 0, you have a negative exponent. So what you need is that this exponent here, what you're familiar with, is that this exponent needs to be positive or 0. So 1 minus 2 gamma has to be bigger than or equal to 0, and then you do 2 gamma, and then gamma is going to be less than or equal to 1/2. So from this scaling argument alone, we know that this kind of inequality can be true with n bounded by m whenever gamma is less than or equal to 1/2. So you could have C gamma to the 1/2, or you could have C gamma to the 1/5, which is an earlier result, not this result up here. Where is it? This result. But an earlier result, someone had proved that this was true as long as you made this kind of assumption. However, Kukovsky and Software has this optimal estimate here, so it's the smallest number. And not only is it optimal, but there's two things about it. First of all, it's the only estimate you can write like C delta to the gamma with without any mention of the size of the norm. You can see this theorem up here doesn't have a mention of the size of the norm. So there's no requirement that n norm is bounded by m. Not only that, but even if you know the result just for n bounded by m, like if you knew this result for only n is bounded by m, you could then infer it for any bounded norm because this inequality is homogeneous, meaning that this side scales linearly in R. Like if I put an R in here, it scales linearly in R. If I put an R in here, it also scales linearly in R because it's R squared to the 1/2, so it scales linearly in R. So both sides are homogeneous. So it's a homogeneous inequality. So you don't even need a boundedness assumption. And if you had a boundedness assumption like this, if you had some kind of n that had bigger than m, then what you could do is just form nr, where r is small, apply nr, this inequality to nr, and then remove it by the scaling, the homogeneity, to get the inequality for n. The point is that once you know that this kind of inequality is true for something like this, then it doesn't matter whether or not you restrict to the norm being bounded or not, because it's just automatically true. This is through the homogeneity of the inequality. So that was all that I wanted to say. This is an introduction to the topic of almost nearly commuting matrices. It's kind of about the ideas that come up, key examples, key theorems, stuff like that. So if you were looking for an introduction, hopefully that's what this was supposed to be. Hope you have a nice day.